Thank you very much for everybody being here, especially under these difficult circumstances again. And once more, I wish you all the best and success, that future will be the way about how well you deal with this. And there's a great future for you guys, and I'm happy to help and contribute. So let me encourage you as much as I possibly can. Today I want to talk about the Mandelbrot set, something that I know about it and something that we don't know about it. So this has been investigated quite a bit, and there are a number of interesting results, and there are a number of open conjectures. And that is, well, and some results are really surprising and remarkable. And some of the, oh yes, that probably should keep. Maybe at the end I should make a drawing contest for you on the Mandelbrot set. There is a unique component in here which contains all the quadratic polynomials z squared plus c for which there exists an attracting fixed point, period 1. There's also one component which is actually a perfectly round circle, which is c, for which the polynomial has an attracting cycle of period 2. For period 3, there are 3 such components. 1, 2, and this little one here. For period 4, there are 6 of them. 1, 2, 3, 4, 5, 6. And then I could continue, but this gets more and more tedious. But there's a pattern to it. One of the patterns is if you have any component of period n, then that means inside you have attracting cycles of period n. Then the multiplier at the periodic n orbit is somewhere in the unit. So there is period whatever, and then the nth iterate has a fixed point. And it's attracting if the derivative along this periodic orbit has absolute value less than 1, so it's in the disk. And one of the nice theorems is this is always diagonal. So each of these hyperbolic components is naturally parametrized by the unit disk in terms of the multiplier map. Okay? And so the boundary of the component is analytic. The boundary, this map, is a homomorphism between the closures. So it makes sense to talk about the boundary point at angle P over Q, which is the point P over Q here, measured in full turns. 0, 1/4, 1/2, 3/4. This is, let me write the multiplier map. For the periodic cycle of period n, you take the derivative, you take the nth iterate, which has a fixed point, and the fixed point is attracting. That means you say f of z, which is nth iterate of the polynomial, so that is Taylor A, then I can expand this at A is at A plus epsilon. This is A plus epsilon times, and I call mu the derivative order terms. And it's attracting if mu is less than 1 in absolute value. And that's exactly this map here. Okay? Make sense to everyone? Okay. Point at whatever angle P over Q, that lifts to a boundary point, corresponding boundary point here. And that is the point of bifurcation where you touch a component of period Q times n. For every such rational angle here. So the simple cases are here, of course, here's angle 0. At angle 1/2, you bifurcate to period 2. At angle 1/3 and 2/3, you bifurcate to period 3, and so on. You see that? It's a rational number between 0 and 1. Any. Over Q, then this point is the touching point of some other component of period Q times N. For the multiplier map, the boundary goes to the boundary, yes. At all the rational boundary points, so there are many of them, they get small because they have to be disjoint. But there is one at all the rational boundary points. Yes. So here for period 3, what I've just sketched up there is obviously period 6. And then there's a little decoration here for period 9 and another one for period 9 in there. And the 9 itself has an 18 and a 27 and so on. It's hard to draw. But that way can produce lots and lots of little further hyperbolic components of all periods. Okay? So these are in some sense the easy ones, but they're also the boring ones. You can get chains, for instance, here there's a chain period 1, 2, 4, then comes 8, 16, the powers of 2. These are natural. I will not describe what I mean, but all the ones that do this is the not so interesting dynamics. If that means to something to you, well, these are the entropy 0 maps. If you want to get interesting dynamics, you want to have positive entropy. For instance, this period 3, once you start bifurcating to something odd, but still, so here there's a limit to the infinity, so to speak, and there's a lot of life afterwards. Maybe the most interesting life. The real Mandelbrot set gets only interesting after to the infinity thing. Okay. And yeah, let's look at the real Mandelbrot set here. There is -2, and I forget what that is. If you look at this interval over the real, then one famous theorem by Fields, medalist Kurt McMullen, that is everywhere here, hyperbolic dynamics, that means periodic components, are open and dense. So on this interval, from here, well, actually the whole Mandelbrot, a real Mandelbrot set. These hyperbolic components, they get small. There are countably many of those. Their union is obviously open, that there's every interval here intersects some of those components. Okay. But that was McMullen, and this, if you take the real line -2, 1/4, so that's the real Mandelbrot set, minus the hyperbolic components. So this is open and dense, so the complementary points are closed and continuous. Hyperbolic component of period 1, 2, 3. These are. So you remove this open collection, and what's left is closed. And it has no interior by this statement. This has positive one-dimensional or length, whatever, length or area. So what's left has no interior points, but still positive length. In fact, in certain intervals, you have most of it. Yes. One-dimensional. Lebesgue measure is housed of maybe up to scaling factors, but they're the same thing. So, a quarter. And you remove countable many open intervals here. So they have so many lengths, you subtract that, and what's left is something distinctly positive, which is rather surprising. Does z squared minus 1.5, I take this map for the specific parameter 1.5, have an attracting cycle. If you're a topologist, you would say all the attracting cycle ones are open and dense. So topologically, probably yes. If you like measure theory, well, the complement has positive length, the probability. But this is not the case. This question is due to my friend John Milner. So, famous mathematician, famous question. And the likely answer is we will never know. Probably we will never know. Unless some smart guys are coming and tell us something that we don't know. Okay, so this is one of the fun questions. Well, for some it's easy to decide. But if you zoom in sufficiently far, then there are intervals on which most of the points are probably non-hyperbolic. The positive measure has to come. Right. I mean, if you find that it has an attracting cycle of period 7,500,009, then you can prove it with finite precision. But if you check up to 5 million and you haven't found anything yet.
Well, at least possibly we could try to count how, what would be the distribution of minimal cycle.
You can, but this is the status of affairs for 20 years or 30 years. We just don't know.
In principle, one of the answers is easy to obtain. Like, if it does have an attracting cycle, could we in principle just run a computation
and people have. And they have not found anything for period up to whichever.
Okay, but if there does exist, then if we keep building bigger and bigger computers, we will find it eventually.
So it's positively semi-decidable. Yes, if you have an attracting cycle, you can compute it with finite precision to do reasonably well. And compute it, yes. And people to try. I want to answer the question by Milner. So of course people have tried. And people with good computers have tried.
Cycle period q times n, which is touching the point.
I haven't proved it. Today, I'm not sure I want to, I'd rather tell you some stories.
So it's not something completely obvious.
It's not particularly difficult. It's in section 6 of the book, but it's not too obvious. But I see some strong entries already in the competition of good Mandelbrot set drawings. Yes, people are making progress. So if you have a math party or something and there are little exercises to do, let's see, that's a nice question to do. Okay, now I will just mention a few things. things which are known or not. We can discuss with some of you how to prove this, but for the actual proofs I want to present today, it's something different that I'm going to. And in some sense, this is not interesting enough. It's a little bit algebraic calculation and then some open mapping. Yeah, it's not too interesting. Let me tell you a few more interesting things. So, of course, every hyperbolic component has analytic boundary. So, the Hausdorff dimension of an analytic curve, Hausdorff dimension of the boundary of any hyperbolic component is 1.
What do you mean by skip the parameterization?
So this map generally extends to a bigger set, to a bigger radius here, bigger radius there. So it's just something which is locally parameterized by an algebraic curve. Exactly, by a local holomorphic map. I will not define Hausdorff dimension. Who of you has heard about Hausdorff dimension? Most of you. Ask the others. It's just a natural concept of dimension. And take it as such. There can be lots of stories about those also, but everything. So, analytic curves are very smooth, have nice dimension. And now one of the nice properties is it is stable under countable unions. So if we take all the hyperbolic components, each of them has analytic boundary, each of them the boundary has dimension 1. And not every dimension, the concept of dimension has this property, but Hausdorff dimension specifically is stable under countable unions.
Maybe I will clarify for myself and for others. So, like a curve, which we're used to, is it? So,
Every curve.
has dimension 1, but I'm not sure if it goes the other way.
Well, I mean, what do you think of the triangle curve? This limiting curves have Hausdorff dimension log 3 over log 2 or log 4 over log 3 or so. This is positive dimension.
But like in the limit, yeah.
In the limit, yes.
So like the curves that we're used to.
Smooth curves, you shouldn't be. Higher dimension. And this is, I mean, you can tell lots of Mandelbrot stories, but this is what he really brought into the game. That you should not think, I mean, he was saying that trees are not cylinders, woods are not spheres, and the coastline of Great Britain, what is the length of the coastline of Great Britain? I mean, perhaps because a certain Hausdorff dimension. So this is a very natural concept to look at. And often it gives you much more interesting answers. In the old days, people would only look at smooth curves, smooth surfaces, and discard everything else as ugly but like solve when somebody says it's ugly or bad. That means they haven't understood it. It means you should investigate it.
It's beautiful, but I think like for many students, those are like more familiar curves. So for this,
Yeah. So I have a nice paper, and I'm happy at some other point to talk about it. Hausdorff dimension, its properties and its surprises. And in the first half of the paper, I introduced the Hausdorff dimension as a very nice and intuitive object, only mysterious and surprising, and beautiful. But this is a little side story. But what I want to show here, or not show, but state also, the Hausdorff dimension of the boundary of the whole Mandelbrot set is 2. So it is a nice thing. It could be topologically still a circle. It's one of the conjectures I want to go to, that the boundary of the Mandelbrot set is, in some sense, a curve. But we know it has Hausdorff dimension 2.
But there are countable hyperbolic components.
Yeah.
There is a lot of, this dimension 2 comes from other parts.
Exactly. So the boundary that you see is, in some sense, negligible. There's something called harmonic measure. If you come from infinity somewhere in a random way, you will not land on the boundary of one of those components that you see. attracting cycle.
So it's clear that
Mm.
there are complementary mechanisms. And we also about complement of hyperbolic. Mandelbrot set without hyperbolic.
So that is what is the Lebesgue, two-dimensional Lebesgue measure of the boundary of the Mandelbrot. No, it's just, so this is a question. Nobody knows anything. That's not quite true. I worked on this ever since I was a graduate student. Still, nobody knows anything. I mean, on this and try to do something. It is not clear. That is another thing I've been working on for the same time. But now I'm working with a colleague in Paris. Hey, need to see this. And we're trying to write a paper, hopefully by the end of the year, to get the best, our plan is to get the best possible estimates of our generation. So that the record of precision should hold for at least a generation, or until somebody does it on a quantum computer, whichever. But we are trying to work really hard, and it's part of, you first have to find the hyperbolic components, and he found, among other things, so I had the record of the period up to 30 with my students, which is polynomial degree 1,000,000, 41, which is 10 to the 12. And that is the biggest polynomial ever factored in world history. So he's the co-author. He has all the data for this. But even that is not good enough for good estimates. So we are working on it, and maybe a few, even less, we have a paper on it with a good answer for this. And this is a surprisingly difficult to compute question. I can give you an answer. So hey, so this equals 1 minus sum n, what is it called? Yeah, an squared. Where this, remember the Mandelbrot uniformizing map equals c minus 1/2 plus sum a and c to the minus n. Remember the power series where all the coefficients can easily be computed and they're all dyadic rational numbers. You plug them in and there is an exact formula. It's not an estimate, it's exact to compute the area of the Mandelbrot set. No, for the boundary we don't know. It's the Mandelbrot set is compact. And so this is an exact formula, but it's a remarkably bad way of computing it. I mean, he has evaluated this, and this is, we get 2 valid digits out of it, maybe 3 or something, even when you have 10 to the whatever coefficients. Incredibly slow. In theory, perfect. And in practice, pretty much useless.
Is there hope for a closed form?
Always. There's always hope for everything. Yes, people had made some conjectures or whatever. So the world is full of almost experts in the Mandelbrot set. And they keep editing the Wikipedia page of the Mandelbrot set. And one day I was sitting down and tried to get rid of the most garbage. And then the next day it was all restored because of vandalism. And okay, do their thing. I first have to finish and publish the book, and then there's a source, and then we can do it. But that's the right order of things.
So is this measure of boundary or the whole set?
This is the, you're right, another one of my mistakes. So Lebesgue measure of the Mandelbrot set is that. And for the boundary, could be 0, could not be.
But it's measurable. It's at least bounded.
It's a compact subset of the plane. That's easy. And I'm very happy to say that the person who knows the most about this is from a friend of mine. So I hope I hope you hear this, yes. With him, I've discussed many times. I mean, it's one of the many beautiful open questions. Need some young people to work on this.
So is this formula factor that
Yeah, this is totally general.
just because it's analytic?
Yeah, this is called the area theorem. That you can look up in Wikipedia. And all the Mandelbrot experts will not touch it. So I think that's correct there. There's no Okay, another of those questions, actually it's, let me question first. Is there an interior component of the Mandelbrot set that is not hyperbolic? So far so good. I've shown you lots of hyperbolic components that have attracting cycles of whatever period. Could it be that there is some mysterious open blob in the Mandelbrot set that has interior and is in the Mandelbrot set, but has no attracting cycle?
Likely no, right?
Not so much space left for that to be.
That doesn't mean much. And this is part, of course, of our investigation. If we have a good estimate for the area of the Mandelbrot set, for the hyperbolic area, then the difference between those two is either in the boundary or in the non-hyperbolic component. And so my tentative title for that paper is Dark Matter in the Universe of the Mandelbrot set. Let's see, we haven't decided on the title of the paper yet. But these are profound open questions.
It is hard to account the area of hyperbolic components, right?
No, hyperbolic components are easy. Estimate for the hyperbolic components. Well, you find the hyperbolic components one way is you find the centers, they define a certain polynomial, you solve this polynomial, and around them you have hyperbolic components. Centers are those where the critical point, where zero is periodic. We discussed that the other day, where c squared plus c squared plus c squared plus c equals 0.
And then you can write down a map from unit disk to this component, and then we have
Yeah.
a formula for area and
So for every component, it's easy.
for some of them all.
This is exactly what we are evaluating. Some supercomputers are working on producing the numerics, and then we are evaluating the rate of convergence, and that is much easier. For the boundaries, for the closed Mandelbrot set, much harder. So I hope I've convinced you that there are some deep and profound questions on this. Okay? Now let me move to the easy side. Easy results that I want to show you. Any questions before I erase? Okay? Everyone? So let me describe how to draw the Mandelbrot set with ruler and compass in an elementary way without knowing pretty much anything. Yes, yes. Or the Babylonians, or let them fight for it, yes. So, from 0 to 1. On the circle, you know, we have the dynamics z maps to z squared. We discussed that the other day also. And I mean, this will be the Mandelbrot set, but area of the disk will go to 0. Everything outside will go to infinity. But the interesting dynamics takes place on the circle. Okay, follow? So let's find periodic points. N equals, what are the boundary points that have period 1, so there are fixed points? Only one, and which point is this? Well, yeah, it's the, let me try to describe it in terms of angle is 0, which is the same thing as 1, because it's a full turn. Okay, so, here it is. Now let's look at period 2. Which one? How many in which one do we have? No, what 1/2 under angle doubling, that's what? It goes to 1, which is 0. It's 2. 1/3 under angling doubling goes to 2/3, which under doubling goes to, you see angles are doubled here. And 2/3 times 2 is 4. So we have angles 1/3 and 2/3. Okay? So let me connect them. No, this is no good. Okay? So, period 3. Seven, more not quite.
Some of them, I think, 6.
6 is better. But 7 is still good.
So there are 7 points that satisfy the equation.
So we want to have 2 to 3 times an angle is the same angle plus an integer. Right? So that means theta times 2 to the 3 minus 1 is an integer. So theta is an integer over here. Okay? And now we can generalize period 3 to period n. Is this. But period 3, we have 1/7, 2/7, 3/7, 4/7, 5/7, 6/7, and then 0 is period 1. They connect the first to the second, the third. Very good. Okay.
It's not constructable by the ruler, but by the ruler.
It's all coming at the same time. Pretty efficient. Can somebody explain to me why they say, may the force be with you?
Why do you say this?
Yes? Huh?
Just from the Star Wars.
Is it Star Wars? Okay, so may the force be with you. So that also means we can stay here quietly. In principle, you can just draw a straight line. In fact, what I've done is I've drawn a straight line, but in the hyperbolic metric. It's topologically the same, but this way the picture looks nicer, and it's easier to draw. There's one more. So what do we get?
15, but some of them don't work.
So let's just, let me use perhaps a different color. 1 over 15, 2 over 15, 3 over 15. 3 over 15 is 1/5, but it doesn't matter. 4 over 15th is here. 4 over 15th is 1/3. And we had it before, so we don't use it again. Then comes 6 over 15 is here. Here, and the whole thing symmetric.
So it's not 8 confirmed, it's more than
There's at least an easy recursive formula. So I connect this one to the next, this one to the next. I connect this one to the next. That is available, but I cannot cross here. And I cross here, and then the rest is easy again. Or do we need to connect them in the first place? I haven't proved anything. So I can say something. I cannot prove everything today. Read this book. Well, partly this is volume 2. So let me, in red, do period 5. 1, 2, 3, 4. I have to think. I think it is 5, 6, 7, 8, 9, 10.
suspiciously well know what fractions are related. Which fractions give you.
Suspiciously.
Yes.
Do you suspect me of having prepared the class?
I don't know. I think there's some pattern. How many points are there in each region?
Oh, but that's something that the ancient Greeks could have done also. So I have to, and then I don't remember. I mean, I have to sort it out a little bit, and I do the same thing. I start with the first one, connect it. In principle, there are 4 candidates, but I connect to the next one, and then this one. And then there is something I could tell you, but maybe it's faster to just do it like this. In principle, you see, this is something which you can do in paper and pencil. Okay, so that is what I've drawn here, Step-Morse algorithm. That's the first step. Step 2, take the limit.
I don't know if Greeks were so good at that.
Well, this was worth for a mathematics to develop after the Greeks. Now you convince us. So, take the limit in the sense that if there is a sequence of such lines that converge to such a limit, then you take the limiting line also. So this is this. So then you take a quotient if, so each of this is a leaf. This thing here is a limit leaf, but it's also a leaf. Or if, let me use green to draw for you a finite polygon. And you see it already coming here. This is a trigon, in fact. So if this is the last green, I have to be nice to it. 9 over 56, 11 over 56, and 15 over 56. So this is a triangle, a finite-sized triangle, also be collapsed to a single point. Okay? So, I take the closed disk and I take this quotient. And by this equivalence relation, all the leaves, including limit leaves, and all finite polygons.
So finite polygons means that there is no leaves inside, right?
It is a finite collection of vertices. More precisely, what I would get, this is my green triangle, and I will get from here a sequence of leaves that I've drawn that converge to it from here, and you converge from there, and you converge from here. Triangle in the sense of the hyperbolic metric of the disk, but it does not correspond to a hyperbolic component of the Mandelbrot set. It rather corresponds to a single point, because we've taken the quotient. Yes, yes. And then the last step is the hardest. Prove that the Mandelbrot set is homomorphic to this quotient. So what we have drawn is the Mandelbrot set. It's just up to homeomorphism, yes. And I want you to be amazed. I've shown you all the complicated properties of this guy. And now it's a very simple paper and pencil algorithm.
Are like the properties of the Mandelbrot set we are like interested in captured by topology only?
You guys, I'll get to this. I want to talk about some of the open conjectures that we are trying to understand. But the topology of the Mandelbrot set indeed is one of the profound questions. And it has relations to many other areas. It's hopefully being proved as we speak, so to say, within the next half year, whatever.
So it's not always
Now what's it? Yeah, what's a challenge to you? But you're competing with this, plus a former PhD student of mine who's not from Kharkiv. But yes, so this is, so in any case, what it is known that there exists a continuous surjection from the Mandelbrot set to what's called the abstract Mandelbrot set. And that's not so very hard to prove. Well, once you understand the Mandelbrot, I mean, this is kind of the introductory topics of the Mandelbrot set. The issue is injectivity.
So in principle, if we pick a point on a matrix set, we can say which polygon corresponds to.
In principle, yes. Yes, yes, yes. Let me give you a question.
I was going to ask if it's obvious that Mandelbrot is not homeomorphic to lattice, but I suppose that is obvious.
The Mandelbrot set is?
It's not homeomorphic to lattice.
Yeah. Justify where this picture is coming from. Needs some proofs also, but in principle, it's not coming out of thin air. I'll keep that picture, and I make space on this side. Than the Mandelbrot set. Is there a volunteer who would like to draw it for me?
The leaves from this picture corresponds to hyperbolic components of Mandelbrot set.
There will, yes. The first correspond to something else, and then yes. Any quick volunteer from Mandelbrot set?
I could try.
Let's see. With the left hand. I've never drawn a Mandelbrot set with my left hand. Yes. Very good. Okay, this is yes, we should. It's just about, yes, so I'm very proud of myself. Let me just get a few things that should be around, and here I want it to be a touching circle. So you focused a little bit on the hyperbolic components. I want to for our friend from period 3 and such, but there is, well, I just want to have this here. There is somebody with period 4 in here. So we know that there is a Riemann map, which we draw in this way, C, the complement of the disk to the complement of the Mandelbrot set. Normalized so that C of infinity is infinity, and C of C divided by C tends to 1 as C goes to infinity. Such is unique. That follows, or you prove that at the same time as you prove that the Mandelbrot set is connected. So, and now you have radial lines here. All kinds of radial lines, whatever. And the images are arrays, which are in the complement of the Mandelbrot set. So you will not be surprised that the ray at angle 0 maps to the positive real line greater than 1/4. Okay? So this is the period 1 under angle doubling. Let's look at this period 2 under angle doubling. Are the two rays 1/3 and 2/3. And their images are this guy somewhere are some curves that near infinity come at angle 1/3, and it goes someplace, and in particular has a limit right here. And the 2/3 one, right here. So the ray at angle 1/3, parameter ray, and the parameter ray at angle 2/3, they land together. And the fact that they land together is indicated by this here, it's black, by this leaf between 1/3 and 2/3. Okay? And so, if I just draw this leaf and take the quotient of the single leaf, then I have a disk on the right and I have a disk on the left that touch at a single point. And that's what I have here. The disk. And as I forget who suspected this, what's this you? That what does it have to do with hyperbolic components? They touch on the boundary of the period. This was period 2, and they touch at the boundary of the period 2 component. Lands at the what's called the root of the period 1 component. And that pattern prevails. So angle 1/7 and 2/7 are rays here and here that land at the root of a period 3 component. And here, 3/7 and 4/7 land together at the root of the real period 3 component. It suddenly makes a lot of sense. Into fibers, that's the word I introduced. Yes?
So this explains where do we get these points to connect hyperbolic components, and therefore I think we can see where we will get hyperbolic components. But we know that there is something else in the Mandelbrot set, and where does it come from?
There isn't so much something else. So there are branch points. Let me draw it down here. It's symmetric. Here, this is a branch point in the sense that 3 rays. So let me draw this minus 9/56 minus 11/56 minus 15/56. It's the same thing I have here, it's a bit too small. And that's exactly this triangle. Collapse that to a point, you have 1, 2, 3 disks that touch at that point, which is this branch point. And since there are limiting like so from all sides, you don't really see disks that touch, but bubbles that converge here from all 3 sides. Yes? Well, you take this algorithm, order by periods, always connect everyone to the next of the same period that's available.
Yes, but that's on this circle.
Yes.
But how do we connect circle with the Mandelbrot?
Oh, here in the Mandelbrot said which ray lands where. That gives me an opportunity to advertise my own PhD thesis. And one of the questions that this thesis answers is, how can you find out? You have a ray angle something. Where does the ray land in the Mandelbrot set? How can you find out without having Adrien Douadi next to you? Of course, but the real goal for this thesis was to compute certain Galois groups in dynamics. So everything connects with everything. It's not what I want to talk about today, but yes, you can do that. So have I convinced you that that this really makes sense to connect to the Mandelbrot? And this is how you find all the hyperbolic components. Now we're discussing about suspicion. What had I prepared? One way is, in order to find which components are which or between which others, one way is to draw this algorithm. So that's one way to draw it. From either ways, I know where the component is. I draw the algorithm. So one thing you have to know, and then you can conclude the other.
But still, we have these points in Mandelbrot set that has closed off dimension 2 that are not boundary points of hyperbolic.
Right.
Do we know that they here will correspond?
So all the pinching happens for periodic angles, which are countable. Or the pairwise pinching. All the polygons you have to show this are dyadic rationals. So it means countably many points, all the rationals can do something. But all the irrational ones, which as you know are most of them, are by themselves.
So maybe not proof, but any arguments that support the idea that at least in neighborhood of these points, this still works. Or do we just see that it works for hyperbolic components and their compounder and hope for the best?
I'm not sure what exactly that means. So for the only input that we have are the periodic ones. And then it's not so hard to prove, well, no, actually I have to take it back. You can have limit leaves of pairs that are not rational. For instance, the Feigenbaum point here. So limit of period 2, 4, 8, 16, and so on. The limit is irrational. But it's still a non-trivial limit. But as soon as that's what I meant to say. If you have 3 or more rays landing together, so if you have some branching, then it must be rational with even the. Okay, if I have time, I want to tell you something entirely different. So here comes some of the fundamental theory of renormalization. And really, all the hard part is renormalization. That's one of the deep and beautiful theories. And polynomial-like maps. Renormalizacja. I think there was fluent Ukrainian, I hope. Renormalisierung in German, Renormalisation in French. And I speak many languages, you know? It's all the same word.
You also hit Polish in the same go.
Which one was it? Okay, so you see, this is truly international. But now somebody advised me to do precision tossing. Only the cup comes back and that can be recycled. This is better. So you have 2 domains, U and V in the complex plane. So they're both simply connected. Of U is contained in V. So here is U, here is V. Something like this. Both simply connected. It's just any 2 Riemann domain. And suppose there is a map F from U to V. That's a proper map. I'm not sure whether you know what a proper map. You can define it many ways. Let me just cheat a little bit and say that the boundary of U maps to the boundary of V. That's good enough for us. And every such proper map has a degree depends on the domain. And it's really interesting when the degree is at least 2. Precise definitions you find in the appendix of this wonderful book. You see that? You have a polynomial of degree d. And then if you have some large circle, take a large circle, it maps the circle of radius r to the d, at least approximately. More precisely, it will not be exact. You start with some radius r, and the pre-image of the circle. If you map forward, then you have to adjust d points that all map to the same image. If you start from the image circle, then it's much nicer, much easier. So if I produce a little hump here, for instance, then here are d humps, which have to be synchronized. By taking pre-images, it's much easier to arrange. Yes, and therefore it's called polynomial-like. And the fundamental theorem due to Doherty and Hubbard is that each polynomial-like map f of degree d, or now say topologically conjugate to a polynomial of degree d. Topological is not good enough, I will change it in a moment. Just like a polynomial. But nobody says this is coming from a polynomial. It could be some rational map, or it could be just a local map or whatever. So this is a very flexible construction. And it is but it captures something that wants to be a polynomial. You know, okay, if you don't know topological or conjugation, then thing is corner, so don't, yeah. But no, I mean, I should tell you, you have a map U to V, this is the map F, and then there is a homomorphism, so that here is some D and D prime, and that's a polynomial. Topological conjugation means there's a homomorphism. You take some presumably complicated dynamical system, and then phi something like changing coordinates. And in changed coordinates, the map is much simpler. And it's really a coordinate change or somehow translation of language. If you have a complicated problem in a complicated language like German, then you translate it into an easy language like Ukrainian, or vice versa. And you have to answer, but of course you have to. It is a change of variables. I would call it change of coordinates, but somehow coordinates are appropriate variables. Okay? And that's exactly, so I can change coordinates, this very flexible map to something quite rigid. Phi. Homomorphism. Moreover, polynomial P is unique. Almost unique. There's a finite choice, doesn't matter. It's unique if the filled-in Julia set of this polynomial-like map, f from u to v, is connected. So the filled-in Julia set are the non-escaping point. So when you iterate, you may stay in u for a while, and at some point you may jump from u to v to the part outside of u, and then you stop. But there may be points, for instance, fixed points or so. Okay? So, and this is the filled Julia set. If that happens to be connected, then the resulting polynomial is almost unique. It's up to a fine change of coordinates, which is always, gives you the same map in different coordinates. And this condition is equivalent to the fact that all critical points of f bits that stay in U. So a critical point is again a point where the derivative vanishes. So you don't have to check all the points and whether it's connected. You just check the critical points. And there are d minus 1 critical points if d is the degree. You just check those d minus 1 points. And if their orbit stays in U all the time, then the Julia set's connected. The filled Julia set's connected. And then the polynomial is unique. Apologies, yes. See you. It's nice to tell him, yes.
So there is always a fixed point, right?
There's always a fixed point, yes.